Hello AP Physics students, it's Mr. Kennedy. Hope everybody's doing great. This little video today is going to help us review the last two units of electricity and magnetism, and then after we're done with this review, it's really just a matter of getting some extra practice in. So this video is going to help us review voltage and then circuits. So I'm going to go over the basics of all of those here, and then it's just time to get ready for the AP test. So let's start in with voltage. So that was unit number 11. And with voltage, I really want to emphasize that you should concentrate on the concept of voltage first. And we spent a lot of time talking about the concept of voltage, and that what it really was sort of a bizarre concept, is energy per charge. So we define voltage as the work or energy per charge, which is a really strange way of saying things because it doesn't seem to make any sense that you would define it that way, but it turns out to be really useful in so many concepts in electricity. For instance, obviously Ohm's law deals with voltage. Remember, it's the energy per charge. Again, I'm not a big fan of the idea of work, but we can think of that as just energy. Now, the definition besides this, besides having work per charge, the other definition you really come across here is that voltage is the negative integral of the electric field. So electric field can be thought of as the slope of the hill you're climbing, and the voltage can be thought of as the height of the hill you're climbing. If you go up a certain hill over a certain distance here, then you will be at a certain height. Now, when we look at a point charge here, if we were to find out what's going on with that, the point charge would be the integral of Q over 4 pi epsilon naught r squared dr. And what we did is we placed the 0 point at infinity. And by doing that, if you take this integral, what you'll end up with is Q over 4 pi epsilon naught r, because the infinite point turns out to be 0 for us. And you could do this for any electric field, but this is the one that's the most common because that's the one of the point charge. Now, this is a scalar. Voltage is a scalar. Electric field is a vector, but voltage is a scalar. And the advice that I would have for you is that when you have, with electricity, when you have scalars, you should put the signs in. Put the signs in there. For vectors, I would not put the signs in. I would just use the arrows and figure out which direction it's going. So in electric field, you'd use a vector to figure out which way it's going. For voltage, you just put the scalars in, put it in. And what's nice about voltage is you pretty much just have to add it all up. That's really all you're doing with voltage, is adding up all the voltage pieces, because it's a lot like energy. With it being a scalar, you don't have to worry about anything else. But again, I would put the signs in. So if you have Q and you want it, if it's negative charge, I'd put negative Q in there. And then go with it that way. Now, one of the things we did, we combined so many pieces together with one nice big chart, which really puts together a lot of the concepts in here. Here we have a force. The force on a charge is Q over 4 pi epsilon naught r squared. Over here we have the electric field. The electric field is Q over 4 pi epsilon naught r squared. Here we have the work that's done, or the energy, which is Q over 4 pi epsilon naught r. And then here you have the voltage, which is going to be Q over 4 pi epsilon naught r. And we wanted to link these four concepts together. And as I talked about before, for vectors, I would use the arrows. Use the arrows of which way vectors point. And these concepts right here are vectors. So this is your vector side of the whole thing. Where this side over here, this is going to be your scalar side. So these are vectors, force and electric field. They point in a particular direction. This is energy and this is voltage. They do not point in a particular direction. So they're just scalar concepts. So these I put signs in on, and these I wouldn't. So how are these linked together? Well, If you want to find the force, you integrate force to find the work. So work is the integral of f dot dx. In this case, we'll say dr. If you want to come backwards, you find the restoring force. The restoring force is the negative partial derivative with respect to r. So that is how you go back and forth. You integrate force, you get work. You take the derivative of energy, you get force. And again, that's why I don't like the idea of work very much, because it's confusing, because this is really energy. In fact, this is the energy it takes to bring two charges together. A negative energy, it's falling in a well. A positive energy, you're trying to bring it to the top of a hill. Here, if I want to take the voltage, just like we did in that last example, I want to go this direction. Voltage is the negative integral of E dot dr. If I want to come back this way now, electric field is the negative partial derivative of voltage with respect to R. So these are complementary ideas, these two pieces. Force is to energy as electric field is to voltage. But then these things are related as well, because force, to get to electric field, we have this little equation that's going to help us, that the force is charge times electric field, because electric field is force per charge. But here we have work, or energy, is going to be charge times voltage. So notice the parallel between those two. This is force per charge, this is energy per charge. And you have that same idea that's on both sides of the, even though these are scalars and these are vectors, you have this very similar idea. But this chart is a nice one because it puts together all of the concepts that you really have with voltage and work and force and electric field, all and how they link together. But again, I would really focus on the concepts, especially with voltage and especially with electric field. What are they? Because they're strange concepts: force per charge and energy per charge. The last thing we talked about with this particular unit was equipotential lines. And equipotential lines are lines of the same voltage. So for instance, if I have a charge, a little plus charge right here, then what I'll have surrounding that is I'll have lines of the same voltage. And these voltage lines should be perpendicular to the electric field lines. If this is a positive charge, then electric field should be pointing out in all these radial directions here. And therefore, this is like looking at a topographical map. And I'd be going up the hill if I'm going here. This tells me which direction the hill's going, but maybe this is, something like 10 volts, maybe this is 15 volts, maybe this is 20 volts. I'm going up the hill. When I go from one line to another, that tells me how much my voltage has changed. Do final minus initial, and it'll make a lot of sense. But these come up sometimes on the free response. When they do, usually they're pretty straightforward problems, but they don't always look that way. They usually look a little bit complicated. So that's your basics of voltage. Remember, it is energy per charge, and try to make sure you understand that concept for yourself. The next unit, which has a ton of stuff in it, is circuits. And that's actually Unit 11. I think I labeled that first one as Unit 11, but Unit 11 is actually circuits. Unit 10 was voltage. And let's go through some really simple things, a lot of equations that show up here. But the first thing we really talked about was moving charges. And current is moving charges. Current is the change in charge over change in time. That is one of our key definitions there. But one other key definition we found that voltage, the thing we just talked about, voltage was current times resistance. This is Ohm's law. If you go through the AP test and you have not used Ohm's law, you made some mistakes. There's no question. It's basically F equals MA of current-based electricity. But then you also have something called power. The power, which is the same thing we had in mechanics, it's still energy per time or work per time, is I times V, or it's I squared R, or it's V squared over R. It's one of those three combinations where R is the resistance in all of these things. So voltage equals current times resistance. In a way, I like to think of it as F equals MA2 because the more force you have, it's not really force, but it's really energy, the more current you'll have, but the more mass, in other words, the more resistance you have, the less current you'll have. And then here, the more you have current and voltage in a circuit, the more power you need to have to make it flow. Now, we could hook up resistors in series and parallel. And in series, the rules are pretty simple. And we're going to see a lot of this is going to come back again. The currents are the same. The voltages add. And the resistance adds. So in series, you have the same current everywhere. The voltages add up. The voltage through every resistor adds up to be the voltage total, and the resistances add up to be the total resistance. In parallel, it's a little different. Here, the voltage are the same because every single branch has their own same connection to the battery. The voltage will be the same. The currents add because each branch should add up to the total current. And then we get 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3. They have that reciprocal addition that comes in. And that's a pretty common thing to start mixing and matching in combination too, that you'd see combos come up. And all of this stuff you actually did in honors physics as well, so none of that is new. One thing that is new is the idea of resistance in a wire and something called the resistivity. Now, we're not going to get too much into it here, but with circuits, resistance is in the wires as well. And the resistance of a wire is rho L over A. Rho is the resistivity, how resistive the material is, and this is the length of the wire, and this is the cross-sectional area. So long, skinny wires have a lot of resistance, where short, thick wires have less resistance. It's not really on the AP test so much, but rho does depend on temperature, where most materials get more resistive when they get warmer. So that happens. But that's not very much on the AP test, so I wouldn't get too worried about that. But again, I would put together some combo circuits. Those show up quite often. But that was all of your resistance stuff, and most of that was from last year. But then there's a second part of this unit. The second part of this unit was all about capacitors. And the capacitance of a capacitor, we say, is the charge per voltage. That is the main rule that you have. It's basically the capacity of the capacitor. And for a parallel plate capacitor, now this could be different for other capacitors, it's K epsilon naught A over D, where epsilon naught is the permittivity of free space, the vacuum permittivity, and then area of the plates, bigger plates will be able to hold more, and the distance between them, the more you put them close together, the stronger your capacitor will be. So how do you make a strong capacitor? You put a lot of plates, or you put the big plates in there, you put them close together, and then you put a material in there called a dielectric, where K is the dielectric constant, and the larger the dielectric constant, the more your capacitor will be able to hold. So this capacitor will hold energy in its electric field. The energy of a capacitor is 1/2 QV, or 1/2 CV squared, or 1/2 Q squared over C. Those are the three main pieces that you have there. Now, with capacitors, they have really similar rules to what you saw with resistors. They're not the same, but they're similar. In series, what you see is that the charge has to be the same in all of the capacitors because they're in series, and it actually doesn't make a complete circuit. The voltages add, but then the last piece of this is capacitors in series add like resistors in parallel. So the capacitance has that 1 over, that reciprocal addition that comes in there. So it adds like this. Now in parallel, For that, the voltage has to be the same everywhere. The charges add, so the charge total must add to the individual branches that are happening there. And then the capacitance just adds. And again, one of the problems that people have is they mix up series and parallel for resistors and capacitors. So just make sure you're being careful with that, and you should be all set. But so there was a resistor side, there's a capacitor side here. And now remember though that current is basically the same thing as charge. It's just charge is flowing. So in series, charges stay the same. Current stays the same. In parallel, voltage stay the same. It doesn't matter if it's a resistor or a capacitor. I think those are the most important rules, that charge and current are the same in series. Voltage is the same in parallel. And then the adding for the other one. So another thing that came up in this unit, and again, like I said, there's a lot of things in this one. Another thing that came up was Kirchhoff's loop rules. Now you're not going to have some giant matrix to solve there, but it is important to know that the sum of all currents in a loop is 0. So whatever goes into, what goes into a junction. So whatever goes into a junction must come out of a junction. The sum of all voltages, that's what I was thinking about there. Sum of all voltages in a loop has to be equal to 0. And this is really conservation of energy. You can't go around a loop and all of a sudden end up with more energy than you started with. Here, this is conservation of charge. You're not going to come out of this without the same charge that you came in there with. Other things to watch out for. Know that you put an ammeter in series and it has very low resistance. Put a voltmeter in parallel and it has high resistance. Why? You put it in series because in series currents are the same. You put this in parallel because in parallel voltages are the same. You want it to be high resistance for voltmeters because you don't want the current to go through there. You want it to be low resistance here so that when it's in series, it won't disrupt the circuit. Some other things I would watch out for. Watch out for the whole split capacitor idea, that you split a capacitor and then it maybe turns into a parallel or series. Inserting dielectrics into capacitors. If you insert a dielectric into a capacitor and it's hooked up to a battery, the voltage stays the same. If it's not hooked up to a battery, then the charge stays the same, so watch out for those. And the last big thing there was RC circuits. And for RC circuits, you're going to have a resistor and then a capacitor. That's where the R and the C come from. And then I'll make a little branch right here. This is the R, this is the C, and this is some voltage. Remember with an RC circuit, when you first turn on the circuit, when I first close this part, then what happens is this capacitor behaves like a wire and the current just flows as V over R. But then as this fills up, then no current will flow. So it'll eventually shut the whole circuit down. Then when I close or open this and close this, then what happens is the capacitor actually runs the circuit, and then what we'll see is that the current will flow as V over R again, and then it will die down. But the rough idea that I give people is to ask yourself, what quantity are you looking for? The quantity, if it is increasing, will look something like this. If it's decreasing, it'll look something like this. So for instance, the current in the beginning, when you first turn it on, you get a lot of current because this behaves like a wire. And then after a while, it dies down. So you use this. Current equals current naught e to the negative t over RC. For instance, the voltage on the capacitor. This would be something that's increasing. The voltage is going to increase on the capacitor. So you'd have this voltage that it's getting to. This is the voltage at any time. And that's the equation because it's going to increase up kind of like it does with air resistance. The time constant involved here is R times C. Don't forget that resistance times capacitance is a measure of time. This is the time it takes to rise to 63% of its total value or fall to 37% of its total value, whatever that might be in the RC circuit. So those are the major concepts in both voltage, which I mistakenly labeled, I think, as unit 11 when it's really unit 10, and then unit 11, which is circuits. So really now we've reviewed all the things that are going to be in the AP test, because there's not going to be unit 12 and 13, which is magnetism and electromagnetic conduction. So you can go through and start practicing as much as you can. The more you practice, the better off you're going to be. All right, everybody, feel free to email me with any questions you may have. That's why I'm here. I'm happy to answer you back and help you with your studying as you're going forward. All right, have a great day, everybody.